This free response problem involves a circuit that contains a battery, some resistors, and an inductor. And an inductor is a coil of wire that's in a circuit. And the key idea with an inductor is understanding the idea that the magnetic flux through a coil of wire, if you have a changing magnetic flux, it will induce a current. A current flowing in a wire generates a magnetic field. So when you have a current flowing through that coil, it generates its own magnetic field through the center of that coil. And so with an inductor, if there's no current in it initially, then when we first try and make current flow through it, it tries to cancel that out. So at the beginning, it acts like an open circuit. It acts like a broken wire. But then once we're having current flowing, after a long time, it allows current to flow freely. It acts just like a wire. And so that's going to be the key idea with part A and part C of this problem. So part A says, determine the current through resistor 1 immediately after the switch is closed. So because there's no current that's flowing initially, there's no current that's in that inductor, so when we first close the switch, it tries to keep current from flowing that way. Again, it acts like an open circuit. And so all we really have for the first part, we can ignore the part that has the inductor. We can treat that as a broken circuit, and we just have a battery connected to two resistors. Those two resistors are in series, so the total resistance is R1 plus R2. The current through resistor 1 is going to be the total current that's flowing in the circuit, and from Ohm's law we have that V equals IR. So the voltage is the voltage of the battery. Our resistance is R1 plus R2. And so if we solve for the current, we get the voltage of the battery divided by R1 plus R2. Again, this is a very simple idea. Once we recognize that we just treat the inductor like a broken circuit, we just have two resistors in series, and it's just a simple series circuit. Part B of the question asks us for the magnitude of the initial rate of change of the current in the inductor. So one of the things that we have to realize is that the resistor R2 and the inductor L are connected in parallel with each other. So the voltage across the inductor is going to equal the voltage across resistor 2. The voltage across resistor 2 is just going to be the current flowing through resistor 2 times R2. So it's our answer to part A times R2. The equation for the voltage across an inductor is given on the AP formula sheet. And it says that the voltage across an inductor is negative L di dt. Again, we're not going to be worrying about the negative sign in this problem because we're just looking for the magnitude of the rate of change. But the quantity L is the inductance of the inductor, and the voltage is going to be L times di dt. We're going to set that equal to the voltage across resistor 2. And so this problem is asking us to find di dt, and so all we end up doing is we divide both sides by L, and we get that di dt equals the voltage across resistor 2 divided by L. That part of the question is not very difficult, but you have to recognize that you know what this equation is. So you either need to know that the voltage across the inductor is negative L di dt, or you need to recognize that that equation is a given equation on the AP formula sheet. The third part of the question says, determine the current through the battery a long time after the switch has been closed. And so the current that's through the battery is the total current that's flowing in the circuit. So if we go back and look at this, we said that at the beginning, the inductor acts like an open circuit. No current flows through it at the beginning. But we said that after a long time, when we're trying to have current flowing through it, after a long time it acts just like a wire. It has zero resistance. And so we just have a regular wire. We can think of this as a regular wire connected here. And so that is shorting out resistor R2. You're going to have the current bypassing R2, and all we have is the battery and resistor 1 connected in series. And so our current is just going to be E divided by R1. Part D asks us to sketch a graph of the current through the battery as a function of time. And so one of the things that's important is we have to recognize that this is not starting at 0. And so again, a very basic question might be just a battery and an inductor and a resistor, and the current starts at 0. They're trying to see if you understand the idea that we have here. So you have your starting current and your current after a long time already from parts A and C. And so our starting current is our answer to part A. It's the voltage of the battery divided by R1 plus R2. And we know that our ending current is going to be the voltage of the battery divided by just resistor R1. And so this is starting off at some value, and it's going to be approaching a value as a limit. It's going to be approaching E over R1 as a limit. And so it starts at this value, and it's going to approach this as a limit. The final question says, sometime after steady state has been reached, so when we've reached that maximum current, the switch is opened. Determine the voltage across resistor 2 just after the switch has been opened. So if we go back and we look at this circuit, we had the switch closed, and so current was flowing. Now when we open that switch, again, we would normally think, okay, the current is going to immediately stop. But because of this inductor, if there was current flowing through it, there was a magnetic field through its center. So there was magnetic flux through the coil. And so when we try and make the current go to 0, Faraday's law and Lenz's law says that it tries to oppose that change. There's a current that gets generated that tries to oppose the change in flux. In fact, the current that's going to be flowing immediately is going to be the same current that was flowing through it right before the switch was opened. That was our answer to part C. What we have now is we have this inductor, and it's going to push current around, and it's going to flow through resistor 2. We have a little loop there. And so to find the voltage across resistor 2, we need to recognize that the current that's flowing through resistor 2 is that current that had been flowing in the inductor right before the switch was opened. Again, that was E over R1. That was our answer to part C. So the voltage across resistor 2 is that current that we had found times resistor 2. And that's the end of the problem. Again, this is a very simple problem if you understand the idea of inductors. And so a lot of the things that get asked on the AP test involve understanding how inductors work immediately after you try and make a current flow through them, a long time after current has been flowing, and then what happens if you try and take that current away. And they will change up different parts of the question. You know, they're not all going to be the exact same things, but they're going to be these same key ideas each time they have these inductor problems.